Trying this again. You might be taking the MIT OpenCourseWare course called The Introduction to CS and Programming Using Python 6.100L on YouTube. You might be thrilled that all of the lectures are available for free on YouTube, but at some point you will have to face the fact that you also need to read a textbook, and that's not on YouTube. But now it is. Now you don't have to leave YouTube to do any part of this. This is the readings associated with Lecture 1. That is Chapter 1, Chapters 2.1 through 2.2. Let's jump in. Getting started. A computer does two things, and two things only. It performs calculations, and it remembers the results of those calculations. But it does those two things extremely well. The typical computer that sits on a desk or in a backpack performs 100 billion or so calculations a second. It is hard to imagine how truly fast that is. Think about holding a ball a meter above the floor and letting it go. By the time it reaches the floor, your computer could have executed more than 1 billion instructions. As for memory, a small computer might have hundreds of gigabytes of storage. How big is that? If a byte, the number of bits, typically 8, required to represent one character, weighed 1 gram, which it doesn't, 100 gigabytes would weigh 100,000 metric tons. For comparison, that's roughly the combined weight of 16,000 African elephants. For most of human history, computation was limited by how fast the human brain could calculate and how well the human hand could record computational results. This meant that only the smallest problems could be attacked computationally. Even with the speed of modern computers, some problems are still beyond modern computational models, such as fully understanding climate change. But more and more problems are proving amenable to computational solution. It is our hope that by the time you finish this book, you will feel comfortable bringing computational thinking to bear on solving many of the problems you encounter during your studies, work, and even everyday life. Now, what do we mean by computational thinking? All knowledge can be thought of as either declarative or imperative. Declarative knowledge is composed of statements of fact. For example, the square root of x is a number y such that y times y equals x. And it is possible to travel by train from Paris to Rome. These are statements of fact. Unfortunately, they don't tell us anything about how to find a square root or how to take trains from Paris to Rome. Imperative knowledge is how-to knowledge, or recipes for deducing information. Heron of Alexandria was the first to document a way to compute the square root of a number. His method for finding the square root of a number, call it x, can be summarized as 1. Start with a guess, g. 2. If g times g is close enough to x, stop and say that g is the answer. Like this guy. 3. Otherwise create a new guess by averaging g and x over g, i.e. g plus x over g divided by 2. 4. Using this new guess, which we again call g, repeat the process until g times g is close enough to x. So let's consider finding the square root of a specific number, 25. 1. Set g to some arbitrary value, such as 3. 2. We decide that 3 times 3, which equals 9, is not close enough to 25. So, 3, we set g to 3 plus 25 over 3, divided by 2, which is equal to 5.67. 4. We decide that 5.67 times 5.67 equaling 32.15 is still not close enough to 25. 5. Set g to 5.67 plus 25 over 5.67 over 2, which equals 5.04. 6. We decide that 5.04 times 5.04 equaling 25.4 is close enough, so we stop and declare 5.04 to be an adequate approximation to the square root of 25. Note that the description of the method is a sequence of simple steps, together with a flow of control that specifies when to execute each step. Such a description is called an algorithm. The algorithm we use to approximate square root is an example of a guess and check algorithm. It is based on the fact that it is easy to check whether or not a guess is good enough. More formally, an algorithm is a finite list of instructions describing a set of computations that, when executed on a set of inputs, will proceed through a sequence of well-defined states and eventually produce an output. An algorithm is like a recipe from a cookbook, such as 1. Put custard mixture over heat. 2. Stir. 3. Dip spoon in custard. 4. Remove spoon and run finger across back of spoon. 5. If clear path is left, remove the custard from the heat and let it cool. 6. Otherwise repeat. The recipe includes some tests for deciding when the process is complete, as well as instructions about the order in which to execute instructions, sometimes jumping to a specific instruction based on a test. So how does one capture the idea of a recipe in a mechanical process? One way is to design a machine specifically intended to compute square roots. Odd as this may sound, the earliest computing machines were in fact fixed program computers, meaning they were designed to solve a specific mathematical problem, e.g. to compute the trajectory of an artillery shell. One of the first computers, built in 1941 by Atanasoff and Berry, solved systems of linear equations, but could do nothing else. Alan Turing's Bombe machine, developed during World War II, was designed to break German Enigma codes. Some simple computers still use this approach. For example, a four-function calculator is a fixed program computer. It can do basic arithmetic, but it cannot be used as a word processor or to run video games. To change the program of such a machine, one has to replace the circuitry. The first truly modern computer was the Manchester Mark I. It was distinguished from its predecessors by being a stored program computer. Such a computer stores and manipulates a sequence of instructions and has components that execute any instruction in that sequence. The heart of such a computer is an interpreter that can execute any legal set of instructions and thus can be used to compute anything that can be described using those instructions. The result of the computation can even be a new sequence of instructions, which can then be executed by the computer that generated them. In other words, it is possible for a computer to program itself. Both the program and the data it manipulates reside in memory. Typically, a program counter points to a particular location in memory, and computation starts by executing the instruction at that point. Most often, the interpreter simply goes to the next instruction in the sequence, but not always. In some cases, it performs a test, and on the basis of that test, execution may jump to another point in the sequence of instructions. This is called flow of control, and is essential to allowing us to write programs that perform complex tasks. People sometimes use flowcharts to depict flow of control. By convention, we use rectangular boxes to depict a processing step, a diamond to depict a test, and arrows to indicate the order in which things are done. Figure 1-1 contains a flowchart depicting an approach to getting dinner. Let's start by opening the fridge, taking out leftovers, then the test, does it smell okay? If test passes, yes, then eat. If test fails, no, put them back in the fridge, start over with a new approach. Returning to the recipe metaphor, given a fixed set of ingredients, a good chef can make an unbounded number of tasty dishes by combining them in different ways. Similarly, given a small, fixed set of primitive features, a good programmer can produce an unbounded number of useful programs. This is what makes programming such an amazing endeavor. To To create recipes or sequences of instructions, we need a programming language in which to describe them, a way to give the computer its marching orders. In 1936, the British mathematician Alan Turing described a hypothetical computing device that has come to be called a universal Turing machine. The machine had unlimited memory in the form of a tape, on which one could write zeros and ones, and a handful of simple primitive instructions for moving, reading, and writing to the tape. The Church-Turing thesis states that if a function is computable, a Turing machine can be programmed to compute it. The if in the Church-Turing thesis is important. Not all problems have computational solutions. Turing showed, for example, that it is impossible to write a program that takes an arbitrary program as input and prints true if and only if the input program will run forever. This is known as the halting problem. The Church-Turing thesis leads directly to the notion of Turing completeness. A programming language is said to be Turing complete if it can be used to simulate a universal Turing machine. All modern programming languages are Turing complete. As a sequence, anything that can be programmed in one programming language, such as Python, can be programmed in any other programming language, such as Java. Of course, some things may be easier to program in a particular language, but all languages are fundamentally equal with respect to computational power. Fortunately, no programmer has to build programs out of Turing's primitive instructions. Instead, modern programming languages offer a larger, more convenient set of primitives. However, the fundamental idea of programming as the process of assembling a sequence of operations remains central. Whatever set of primitives you have, and whatever methods you have for assembling them, the best thing and the worst thing about programming are the same. The computer will do exactly what you tell it to do. Nothing more, nothing less. This is a good thing, because it means that you can make the computer do all sorts of fun and useful things. It is a bad thing, because when it doesn't do what you want it to do, you usually have nobody to blame but yourself. And you should be ashamed. There are hundreds of programming languages in the world. There is no best language. Some would disagree. Different languages are better or worse for different kinds of applications. MATLAB, for example, is a good language for manipulating vectors and matrices. C is a good language for writing programs that control data networks. PHP is a good language for building websites. And Python is an excellent general-purpose language. Each programming language has a set of primitive constructs, a syntax, a static semantics, and a semantics. By analogy with a natural language, such as English, the primitive constructs are words. The syntax describes which strings of words constitute well-formed sentences. The static semantics defines which sentences are meaningful, and the semantics defines the meaning of those meaningful sentences. The primitive constructs in Python include literals, such as the number 3.2, or the string ABC, and infix operators, such as the plus sign or the forward slash for division. The syntax of a language defines which strings of characters and symbols are well formed. For example, in English, the string cat dog boy is not a syntactically valid sentence because English syntax does not accept sentences of the form noun followed by a noun followed by a noun. In Python, the sequence of primitives 3.2 plus 3.2 is syntactically well formed, but the sequence 3.2 space 3.2 is not. The static semantics defines which syntactically valid strings have a meaning. Consider, for example, the strings he run quickly and I runs quickly. Each has the form pronoun, regular verb, adverb, which is a syntactically acceptable sequence. Nevertheless, neither is valid English because of the rather peculiar rule that for a regular verb, when the subject of a sentence is first or second person, the verb does not end with an S, but when the subject is third person singular, it does. So these are examples of static semantic errors. And there's a conversation there to be had about vernaculars and dialects and stuff, and I don't take that as criticism of like... Anyway, the semantics of a language associates a meaning with each syntactically correct string of symbols. It has no static semantic errors. In natural languages, the semantics of a sentence can be ambiguous. For example, the sentence, "I cannot praise this student too highly," can be either flattering or damning. Programming languages are designed so that each legal program has exactly one meaning. Though syntax errors are the most common kind of error, especially for those learning a new programming language, they're the least dangerous. Every serious programming language detects all syntactic errors and does not allow users to execute a program with even one syntactic error. Furthermore, in most cases, the language system gives a sufficiently clear indication of the location of the error that the programmer is able to fix it without too much thought. Identifying and resolving static semantic errors is more complex. Some programming languages, such as Java, do a lot of static semantic checking before allowing a program to be executed. Others, such as C and, alas, Python, do relatively less static semantic checking before a program is executed. Python does do a considerable amount of semantic checking while running a program. If a program has no syntactic errors and no static semantic errors, it has a meaning, i.e., it has semantics. Of course, it might not have the semantics that its creator intended. When a program means something other than what its creator thinks it means, bad things can happen. What might happen if the program has an error and behaves in an unintended way? Well, it might crash. That is, stop running or produce obvious indication that it has done so. In a properly designed computing system, when a program crashes, it does not damage the overall system. Alas, some very popular computer systems don't have this nice property. Almost everyone who uses a personal computer has run a program that has managed to make it necessary to reboot the whole system. It might keep running, and running, and running, and never stop. If you have no idea of approximately how long the program is supposed to take to do its job, this situation can be hard to recognize. It might run to completion and produce an answer that might or might not be correct. Each of these outcomes is bad, but the last one is certainly the worst. When a program appears to be doing the right thing, but isn't, bad things can follow. Fortunes can be lost. Patients can receive fatal doses of radiation therapy. Airplanes can crash. Whenever possible, programs should be written so that when they don't work properly, it is self-evident. We will discuss how to do this throughout the book. Finger exercise. Computers can be annoyingly literal. If you don't tell them exactly what you want them to do, they are likely to do the wrong thing. Try writing an algorithm for driving between two destinations. Write it the way you would for a person, and then imagine what would happen if that person were as stupid as a computer. You might not have to imagine. And, and executed the algorithm exactly as written. For an amusing illustration of this, take a look at the video https://www.youtube.com/watch?v=fn2rm-chkuin and &t equals 24s. Terms introduced in chapter, let's review. Declarative knowledge, imperative knowledge, algorithm, computation, fixed program computer, stored program computer, interpreter, program counter, flow of control, flow chart, programming language, universal Turing machine, Church Turing thesis, halting problem, Turing completeness, literals, infix operators, syntax, static semantics, semantics. Deal with footnotes on your own time, I think, actually. I'm just going to skip dealing with them. Alright, and then it's chapter 2 up to and including 2.2 and that'll be the end of the reading for Lecture 1. Introduction to Python. Though each programming language is different, though not as different as their designers would have us believe, they can be related along some dimensions. Low level versus high level refers to whether we program using instructions and data objects at the level of the machine, such as move 64 bits of data from this location to that location, or whether we program using more abstract operations, such as pop up a menu on the screen, that have been provided by the language designer. General versus targeted to an application domain refers to whether the primitive operations of the programming language are widely applicable or are fine-tuned to a specific domain. For example, SQL, also pronounced SQL, is designed for extracting information from relational databases, but you wouldn't want to use it to build an operating system. Interpreted versus compiled. Python is interpreted. This refers to whether the sequence of instructions written by the programmer, called source code, is executed directly by an interpreter, or whether it is first converted by a compiler into a sequence of machine-level primitive operations. In the early days of computers, people had to write source code in a language very close to the machine code that could be directly interpreted by the computer hardware. There are advantages to both approaches. It is often easier to debug programs written in languages that are designed to be interpreted, because the interpreter can produce error messages that are easy to relate to the source code. Compiled languages usually produce programs that run more quickly and use less space. In this book, we use Python. However, this book is not about Python. It will certainly help you learn Python, and that is a good thing. What is much more important, however, is that you will learn something about how to write programs that solve problems. You can transfer this skill to any programming language. Python is a general-purpose programming language you can use effectively to build almost any kind of program that does not need direct access to the computer's hardware. Python is not optimal for programs that have high reliability constraints because of its weak static semantic checking, or that are built and maintained by many people or over a long period of time, again because of the weak static semantic checking. Python does have several advantages over many other languages. It is a relatively simple language that is easy to learn. It is. Because Python is designed to be interpreted, it can provide the kind of runtime feedback that is especially helpful to novice programmers. A large and growing number of freely available libraries interface to Python and provide useful extended functionality. We use several of these libraries in this book. We are ready to introduce some of the basic elements of Python. These are common to almost all programming languages in concept, though not in detail. This book is not just an introduction to Python. It uses Python as a vehicle to present concepts related to computational problem solving and thinking. The language is presented in dribs and drabs as needed for this ulterior purpose. Python features that we don't need for that purpose are not presented at all. We feel comfortable about not covering every detail because excellent online resources describe every aspect of the language. We suggest that you use these free online resources as needed. Python is a living language. Since its introduction by Guido van Rossum, it's a hard G in Dutch that's a little bit different than how it's not like the Italian Guido, so it's a little bit hard for me to get it right, but it has undergone many changes. For the first decade of its life, Python was a little known and little used language. That changed with the arrival of Python 2.0 in 2000. In addition to incorporating important improvements to the language itself, it marked a shift in the evolutionary path of the language. Many groups began developing libraries that interfaced seamlessly with Python. And continuing support and development of the Python ecosystem became a community-based activity. Python 3.0 was released at the end of 2008. This version of Python cleaned up many of the inconsistencies in the design of Python 2. However, Python 3 is not backward compatible. This means that most programs and libraries written for earlier versions of Python cannot be run using implementations of Python 3. By now, all of the important public domain Python libraries have been ported to Python 3. Today, there is no reason to use Python 2. Alright. Installing Python and Python IDEs. Once upon time, programmers used a lot of typos in this text. Programmers used general-purpose text editors to enter their programs. Today, most programmers prefer to use a text editor that is part of an integrated development environment, an IDE. The first Python IDE, IDLE, idle, came as part of the standard Python installation package. As Python has grown in popularity, other IDEs have sprung up. These newer IDEs often incorporate some of the more popular Python libraries and provide facilities not provided by idle. Anaconda and Canopy are among the more popular of these IDEs. The code appearing in this book was created and tested using Anaconda, which is free and it's cool. IDEs are applications just like any other application on your computer. Start one the same way you would start any other application, e.g. by double-clicking on an icon. If you needed that explained to you, you might want to go back to a little bit basics a little bit sooner than this sort of material. All of the Python IDEs provide a text editor with syntax highlighting, auto-completion, and smart indentation, a shell with syntax highlighting, and an integrated debugger, which you can safely ignore for now. This would be a good time to install Anaconda or some other IDE on your computer so that you can run the examples in the book and, more importantly, attempt the programming finger exercises. To install Anaconda, go to anaconda.com/distribution and follow the instructions. Once the installation is complete, start the application Anaconda Navigator. A window containing a collection of Python tools will appear. The window will look something like Figure 2-1. For now, the only tool we will use is Spider. When you launch Spider, by clicking on its launch button, of all things, a window similar to Figure 2-2 will open. Sort of like that. I mean, this, yeah. The pane on the lower right of Figure 2-2 is an IPython console running an interactive Python shell. You can type and execute Python commands in this window. The pane of the upper right is a help window. It is often convenient to close that window by clicking on the X so that more real estate is available for the IPython console. The pane on the left is an edit window into which you can type programs that can be saved and run. The toolbar at the top of the window makes it easy to perform various tasks such as opening files and printing programs. Documentation for Spider can be found at spider-ide.org. And this is the last part of the readings for first lecture 2.2, the basic elements of Python. A Python program, sometimes called a script, is a sequence of definitions and commands. The Python interpreter in the shell evaluates the definitions and executes the commands. It evaluates definitions, executes commands. We recommend that you start a Python shell, e.g. by starting Spider, now, and use it to try the examples contained in the rest of this chapter, and for this matter, in the rest of the book. A command, often called a statement, instructs the interpreter to do something. For example, the statement print, followed by a parenthetical statement in which the string Yankees rule is written, inside quotes, instructs the interpreter to call the function print, which outputs the string Yankees rule, to the window associated with the shell. The sequence of commands, print Yankees rule, print the string but not in Boston, print the string Yankees rule, followed by a comma and a space, and then another string but not in Boston, causes the interpreter to produce this output. Text on 3 separate lines, this string, then this string on a second line, then this string and this string next to each other on the third line, right? Notice that 2 values were passed to print in the third statement. The print function takes a variable number of arguments separated by commas and prints them, separated by a space character, in the order in which they appear. Objects, expressions, and numerical types. Objects are the core things that Python programs manipulate. Each object has a type that defines what programs can do with that object. Types are either scalar or non-scalar. Scalar objects are indivisible. Think of them as the atoms of the language, in the classic original sense of the word atom, even though atoms themselves are divisible. Non-scalar objects, for example strings, have internal structure. Many types of objects can be denoted by literals in the text of a program. For example, the text 2 is a literal representing a number, and the text, quotation marks around ABC, is a literal representing a string. Python has 4 types of scalar objects. Int, int, is used to represent integers. Literals of type int are written in the way we typically denote integers, such as -3, or 5, or 10,002. Float is used to represent real numbers. Literals of type float always include a decimal point, such as 3.0, even though it's a whole number. It's a float because there's a decimal point, or 3.17, or -28.72. It is also possible to write literals of type float using scientific notation. For example, the literal 1.6e3 stands for 1.6 times 10 to the third power, i.e. it is the same as 1600.0. You might wonder why this type is not called real. Within the computer, values of type float are stored as floating point numbers. This representation, which is used by all modern programming languages, has many advantages. However, under some situations it causes floating point arithmetic to behave in ways that are slightly different from arithmetic on real numbers. We discussed this in section 3.3. Bool, B-O-O-L, is used to represent the Boolean values true and false. None, the capital N, is a type with a single value. We will say more about none in section 4. Objects and operators can be combined to form expressions, each of which evaluates to an object of some type. This is called the value of the expression. For example, the expression 3 plus 2 denotes the object 5 of type int, and the expression 3.0 plus 2.0 denotes the object 5.0 of type float. The equal operator, 2 equal signs smushed up together, is used to test whether 2 expressions evaluate to the same value. And the bang equal, exclamation point followed by an equal sign, the not equal operator, is used to test whether 2 expressions evaluate to different values. A single equal sign means something quite different, as we will see in section 2.2.2. Be forewarned, you will make the mistake of typing the equal sign when you meant to type 2 of them. Keep an eye out for this error. In a Spider console, something that looks like in 1 in square brackets, colon, is a shell prompt, indicating that the interpreter is expecting the user to type some Python code into the shell. The line below the prompt is produced when the interpreter evaluates the Python code entered at the prompt, as illustrated by the following interaction with the interpreter. So like, if somebody typed in 3 and pressed enter, then you get the output, first output 3. they typed in the expression 3 plus 2, then you get output number 2, 5. If you typed in 3.0 plus 2.0 and pressed enter, you get output 3, the float 5.0. And if you typed 3 not equal 2, then you get the fourth output, true. That this comparison of two expressions, it is not equal. Indeed, these two expressions are not the same thing, so you will get the Boolean value true in response. The built-in Python function type can be used to find out the type of an object. So, like all functions, they have a parenthetical statement smushed up against them on the right side, into which you can pass an argument, pass something into them. So you're calling the type function with the value 3 passed in as argument, means that the type function will be called on what you've given to it. And in this case, you get an output number 5 telling you what you passed in here is an integer. And if you did that with a float, it'll tell you what you passed in was a float. Operators on objects of type int and float are listed in figure 2-3. The arithmetic operators have the usual precedence, like PIMDAS. For example, the star, multiplication operator, binds more tightly than plus, the addition operator. So the expression x plus y star 2 is evaluated by first multiplying y times 2, and then adding the result of that to x. The order of evaluation can be changed by using parentheses to group sub-expressions, such as x plus y in a parenthetical statement times 2 will first add x to y and then multiply the result of that by 2, just like in regular arithmetic. I think maybe just pause the video and look at figure -.3 if you want to. The primitive operators on type bool are and, or, and not. A and B is true if both A and B are true and false otherwise. A or B is true if at least one of A or B is true and false otherwise. They have to both be false for that to be false. Not A is true if A is false, if the value assigned to A is the Boolean value false, and false if A is true. If the value assigned to A is the Boolean value true, then not A is obviously going to be false, right? 2.2.2 Variables and assignment variables provide a way to associate names with objects. I just wasn't sure if I was still reading this, but yeah, I guess it's all part of 2.2. Consider the code. Pi. Single equal sign. We mentioned that we'd get to this. 3. Radius equal 11. Area equal pi times, in parentheses, radius star star 2, which means radius to the second power. Probably should have read that table earlier. Hell. In fact, we'll do this. Okay. Figure 2.3 operators on types int and float. I plus j. This is the sum of I and j. If I and j are both of type int, the result is an int. If either is a float, the result is a float. I minus j is I minus j, and the same is true. If either is a float, the result will become a float. I times j, or I star j, is the product of I and j. Same. If they're both of type integer, the result will be an integer, but if either one is a float, then the result will be float. I / j is floor division. For example, the value of 6 floor divided by 2 is the integer 3, and the value of 6 floor divided by 4 is the integer 1. The value is 1 because floor division returns the quotient and ignores the remainder. if j equals 0, an error occurs. So, like, you can't floor divide by 0 any more than you can divide by 0. I/j, just a single slash, that's just division. And this will always return a float, even if it's a whole number. It will be, number 0.0. And I, the percentage sign, j, would be pronounced I mod j or I modulo j. This will just return the remainder whenever the integer I is divided by the integer j. Modulo will just give you the remainder of that. And I star star j is I raised to the power j. It's the exponent, sort of like you might use a caret otherwhere, or in other places. Where was I? Okay, so yes, that's why radius star star 2 means radius squared in this code, right? And radius equals 14. The code first binds the names pi and radius to different objects of type int. Because that's what the single equal sign does, is this in Python is not saying, it's not the statement pi is equal to 3. It is saying, essentially, make pi equal to 3. Bind or assign the value 3 to the variable pi. So simply by typing out the name, a new name of a new variable, that is in Python the creation of a new variable, and then you must set it equal to some value. You'll say, I create radius, and I will set it equal to this integer value, 11. And then if you, at any other point later in the code, use the same variable name and equal sign any other value, this will update and give it a new value. That anywhere after you said radius equals 14, now radius will equal 14 instead of the 11 that you gave it earlier. The code first binds the names pi and radius to different objects of type int. It then binds the name area to a third object of type int. This is depicted on the left side of figure 2-4. Assignment, assignment, assignment. Bada bing, bada boom. It was assigned to 11, then later in the code, it's assigned to 14. Same name over here, right? If the program then executes radius equals 14, the name radius is rebound to a different object of type int, as shown on the right side of figure 2-4. Note that this assignment has no effect on the value to which area is bound. It is still bound to the object denoted by the expression 3 times 11 to the second power. So that's important. The value of area, after we've defined the value of pi and the value of radius here, then we use those variables in the process of creating and assigning the value to the variable area. Area equals pi times this variable squared. And then after we assign this value to this new variable area, then it's after that, later in the code, that we change the value of the variable radius. But that won't change the value of the variable area. It will retain the value that it had at this point in the code, okay? Unless you update it after that. Now, in Python, a variable is just a name, nothing more. Remember this. It is important. An assignment statement associates the name to the left of the equal symbol with the object denoted by the expression to the right of the equal symbol. Remember this too. An object can have more than one, or no name associated with it. Perhaps we shouldn't have said a variable is just a name. You just told me to remember that. Despite what Juliet said, names matter. Programming languages let us describe computations so that computers can execute them. This does not mean that only computers read programs. As you will soon discover, it's not always easy to write programs that work correctly. Experienced programmers will confirm that they spend a great deal of time reading programs in an attempt to understand why they behave as they do. It is therefore of critical importance to write programs so that they are easy to read. Apt choice of variable names plays an important role in enhancing readability. Consider the two code fragments. We've got a variable a. We set it equal to the value 3.14159, the float value. The variable pi, which we set equal to the value 3.14159. Variable b. Oh wait, I was saying there's two sort of separate. I see what they're trying to do here. So we have a, b, and c, and we've got over here pi, diameter, and area. And if you notice that it's the exact same things. The variable a is exactly the same as this variable pi. Exact same value and everything. As far as Python is concerned, the code fragments are no different. When executed, they will do the exact same thing. To a human reader, however, they are quite different. When we read the fragment on the left, there is no a priori reason to suspect that anything is amiss. However, a quick glance at the code on the right should prompt us to suspect that something is wrong. It's not diameter, it shouldn't be diameter squared, it should be radius squared. But unless we really thought about this and read that very carefully, if you see c equals a times b to the second power, you have no idea that this mistake was made. Either the variable should have been named radius rather than diameter, or diameter should have been divided by 2.0 in the calculation of the area. In Python, variable names can contain uppercase and lowercase letters, digits, although they cannot start with a digit, and the special character underscore. Python variable names are case sensitive, so Romeo, capital R, and Romeo, all lowercase, are different variables. Finally, a few reserved words, sometimes called keywords in Python, that have built-in meanings and cannot be used as variable names. I guess I meant to say there are a few, right? Different versions of Python have slightly different lists of reserved keywords. The reserved words in Python 3.8 are and as, assert, async, await, break, class, continue, def, del, elif, else, except, false, finally, for, from, global, if, import, in, is, lambda, non-local, none, not, or, pass, raise, return, true, try, while, with, yield. This is supposed to say yield, not yield. Another good way to enhance the readability of code is to add comments. Text following the symbol, the hash, or pound sign, is not interpreted by Python. For example, we might write, so here we've got a whole bunch of variables that we're setting equal to their respective values, and after some of these, so we've got the variable side, we assign the value 1 to it, and in the same line, with the hash sign, starting with the hash sign, I'm trying to figure out how to phrase that. In the same line, we can write this whole comment that is just for humans to read, that the interpreter won't do anything with, so long as we prepend the hash sign. It becomes a comment. Okay, we can put them on lines of their own, or anywhere in another line of code, as long as we get that hash sign in front of it. Python allows multiple assignment. The statement x, space y equals 2, space 3 will bind x to 2 and y to 3 simultaneously. All of the expressions on the right-hand side of the assignment are evaluated before any bindings are changed. This is convenient since it allows you to use multiple assignment to swap the bindings of two variables at the same time. For example, the code x, space y equals 2, space 3 followed on another line by x comma space y equals y comma space x, if you then print the string x equals and then the variable x, and then on a new line print this string y equals followed by the value of the actual variable y, this will print x equals 3 and y equals 2. Because you start by assigning 2 to x and 3 to y, but then you simultaneously swap them out by saying, well, now I'm going to make x equal to what y currently equals and y equal to what x currently equals, and it will comfortably swap them out. Whereas if you had to do that one at a time, like you set x equal to y first, then you would make x equal 3, and then when you went to try and change y set equal to x, well, it would still be 3 because you've already updated the value of the variable x to 3 too, right? You need to be able to swap them simultaneously in order for this to work. So it is very convenient. All right. That's all the reading for lecture 1.